All right, good afternoon, everyone. Let's get started. Hope everyone enjoyed their break, and I'm sure you are all very happy to come back to 1805 and doing test 2. So, where we left off before the break, if we just go back, we were looking at analyzing algorithms, and the last thing we did was we analyzed this maximum algorithm. So to refresh your memory, you're given a sequence of numbers a1 through an, and you'd like to pick the largest one. And what we were counting was the number of comparisons it took to compute the maximum. And we decided that the answer was 2n minus 1. Exactly 2n minus 1 comparisons are needed or are used by this algorithm to compute the maximum. So that's where we were last time. We have a few other algorithms, though, that I'd like to analyze. And one of those is linear search. Wrong color. What I'd like to do is an analysis of linear search. So this is an algorithm we already saw last class. This is to find something in a list. So the way it works is this. Or maybe we didn't do this last class. I don't remember. Did we do linear search last class? No? Okay, well, we're going to do it now. All it is I want to find out whether or not something is in a list. So let's say I have the sequence a1 through an, and I would like to know if some value I is in there. So it additionally takes some element x, and I would like to know the index that x is at. Let's put it that way. So if x is the second thing in the list, it will return 2 because it's the second thing. Okay, and if it's not in the list, it can return not found or something like that. So the way it works is this. It's pretty straightforward. You just look at everything in the list. So for I gets 1 to n, I do the following. I check to see if ai is equal to x, and if it is, then I return I. And if I get all the way to the end of the list and I didn't find it, I just return not found. So this is the straightforward algorithm to find if an element x is in the list, and if it is, what index it's at. Yeah?
But that'll only work for, like, if an x is in the list twice, it'll only give you the first one.
Right, yes. So it'll return the first index of x in this list. That's a correct analysis. Other questions about this? So I'd like to do the same kind of thing again. I would like to count the number of comparisons I do when I call linear search. So what you do, just like last time, is you look to see where are the comparisons. There's one comparison here, right? Checking to see if something is equal to something else is a way of comparing. The other comparisons happen in the for loop, because I need to check that I is less than n, and less than or equal to n, sorry. And I also do an extra plus 1 to leave the loop, because when I equals n plus 1, the comparison will fail. So there's always that one extra comparison you use to exit the loop. So let's see how many comparisons this takes. Well, I'm doing one comparison inside the loop, and I'm doing one comparison, to define the loop. So what we end up with is some number of iterations. That's going to be something. And the number of comparisons per iteration well, that's a little bit easier. We do one comparison here and one comparison here in the for loop. So there's 2 comparisons per iteration, and there is one comparison to exit. So all we need to figure out is the number of iterations that this for loop does. How many iterations of this for loop are there? Yep. It depends. Yeah, it depends on, well, if x is even in there at all, and if it is in there, how early in the list is it? So if x is equal to a1, then you don't need to do very many comparisons at all. But if x isn't in the list anywhere, then you need to look at every single element in the list. So the number of iterations you do will be between 1 and n. Right? You do 1 iteration if you're very lucky and it happens to be the first thing in the list. You do n iterations if you're very unlucky and it happens to, say, not be in the list at all, or if it's the last thing in the list. So the number of iterations will be anywhere from 1 to n. That's what can happen. All right, so remember, we're interested in the worst case analysis of algorithms. So yeah, you can talk about the best case analysis of algorithms, that's fine. That's usually not too interesting. The worst case is what we're interested in because we want to be able to provide a guarantee that says no matter what happens, our algorithm won't take longer than something. Okay, that's something that we want to try to figure out. So what's the worst thing that can happen? Well, the worst thing is that it goes through all n iterations and it isn't there. Right? So the worst thing that can happen is it goes through all n iterations. And if that's the case, well then it goes through n iterations, it does 2 comparisons in each iteration, and then there's also that last comparison to exit the loop. Does that make sense? So this is the number of comparisons in the worst case. All right. If you wanted to do the best case, what would the best case here be? 2, 3. So we need 1 comparison to check to make sure that 1 is less than n. And we need 1 comparison to check to make sure that AI, or A1, is equal to x. And we can return right away. We don't actually need to do that last comparison because there's not another iteration of the for loop to go into. Okay? This describes what happens when you compare to everything in the for loop and you need that last comparison to exit it because it's not there. Right? That's the absolute worst thing that could happen. The best thing that could happen would be 2 comparisons. But that's not very interesting. Right? If you were trying to budget something, you wouldn't want to budget the least amount of time. Right? If you're looking for a budget to buy a house, it's not very useful to say, oh, I'll need at least $1. For sure, I'll need at least $1. That's not going to be very helpful to the bank. Yeah?
Wouldn't the empty list be a faster?
Right, so in that case, it becomes kind of somewhat philosophical about what the input is. As far as non-empty lists go, yes, it's 2. If it's an empty list, then it's 1 comparison to say it wasn't found. That's true. Yeah, and the 1 comparison that gets made is checking to see if I, which is 1, is less than or equal to 0, which is false. Other questions? All right, so notice this is very similar to maximum finding in the sense that the amount of comparisons required looks like a line. Right? If we go back to max finding from last lecture, it was 2n minus 1. And this thing here is 2n plus 1. So these algorithms behave basically the same. Right? If you ran these 2 algorithms, they would take about the same amount of time on lists that were about the same length. Right? They only differ by 2 comparisons in the worst case. Right? But for some lists, linear search will execute faster if we're lucky and the thing we're searching for is early on in the list. Maximum finding, however, that's always going to take the same amount of time for a list of a given size, because I can't help but look at every single thing in the list. Whereas for linear search, I might get lucky and I might not have to look at everything in the list. Is that difference clear? All right. So now we're ready to start analyzing some interesting algorithms. So let's do the analysis of bubble sort. So to refresh your memory, I will give the code again. The way it works is this. I have bubble sort A1, A2, A3, all the way up to AN. And I say for I gets 1 to n minus 1, do the following. For j gets 1 to n minus I, do the following. If they're out of order, so aj is bigger than aj plus 1, then I swap them. Right, that's what I was interested in. And again, what I'd like to do is count the number of comparisons that I do. You can analyze this algorithm other ways, by the way. You don't just have to count comparisons. You might want to count swaps, for example. That's perfectly valid, but it's not what we're going to do here. Today, we want to count comparisons. So where do the comparisons occur? Well, let's see. There's one obvious one, right? If you see a greater than sign, that's probably going to be a comparison. So there's one there. There's also one in the for loop, plus 1 to exit it. And there's one in this for loop, plus 1 to exit it. So if you're analyzing an algorithm, this is the first thing you should do. You should find out where the operations you care about occur. I care about comparisons, so I look for the comparisons. And I like to circle them in blue. All right. So now, I need to write down some way of describing what's happening. And if you think back to when I started talking about summations, I said summations and for loops are somehow very related, right? Because you can write a summation as a for loop. You can do the exact same thing here. But before we go there, I just want to describe what's happening in words. So we have a couple loops here. I'll call this loop here the outer loop. I'll call this loop here the inner loop. All right, so the outer loop, how many iterations does it go through? N? Other guesses? N minus 1. So remember, when you want to know the number of iterations of a for loop, or equivalently the number of terms in a summation, it's the top thing minus the bottom thing plus 1. So this is n minus 1 minus 1 plus 1. So n minus 1. And this makes sense, right? If it was for I gets 1 to 10, that's 10. Here we have n minus 1, so the answer is n minus 1. It goes through n minus 1 iterations. All right. For every one of those iterations, the inner loop goes through how many iterations? N minus I. Is that just the answer? Yeah. So let's just count the inner ones. So really what I'm asking is there a plus 1, a minus 1, or nothing? Is it just n minus I? So it's the top thing minus the bottom thing plus 1. So it's n minus I minus 1 plus 1. So it's just n minus I. All right. Inside the inner loop, how many comparisons do I do? I do one inside and then one during the loop. So each inner iteration does one comparison. Okay. All right, so that's fine. I also have a comparison here. So I'll just say plus 1 comparison, plus 1 comparison, plus 1 comparison. And then to leave the inner loop, I have a plus 1. And then to leave the outer loop, I have another plus 1. So if you're careful, you could just sit down and reason this out just from this. But I don't really like to think that way. Maybe it's not so bad for a bubble sort, but it's easy to get confused this way. So instead what I'll do is I'll translate this algorithm to a sum. I have my outer sum here, and it goes from I equals 1 to n minus 1. And inside that, I have my inner sum, and that goes from j equals 1 to n minus I. And how many comparisons do I do there? Well, I do 1 in my if statement, and then 1 in my for loop. So it's 2. And then I need 1 more to exit, and that's to exit the inner loop. And then 1 more to exit the outer loop. Okay? So what I have here is this. This 2 comes from the fact that I have the inner for loop, and it comes from the fact that I have the if statement. This plus 1 comes from exiting the inner loop, and this plus 1 comes from exit the outer loop. Is it clear where everything came from there? Yep.
Are you missing n comparisons that the other discussed?
That's right here.
Okay.
So I do 1 comparison for each one of those things. Why? Because I do 1 to check to see if this is greater than, and then the other is to check to see that j is less than or equal to n minus I. Other questions? All right. So what we really want to do then is solve this sum. That's what we'd like to do. And if we can solve this sum, then we'll have a nice expression for the number of comparisons made. So let's do that. The way we solve sums, as we all remember, is to work from the inside out. So the sum from j equals 1 to n minus I of 2, what's that going to be equal to? Well, each term is 2, so that's a constant, and there's n minus I terms. So the sum is going to be 2 times n minus I. And then I also have a plus 1 out here. And I still have my plus 1 out there. So now I've made some progress. Let's see what else I can get. The sum from I equals 1 to n of 2n minus 2i plus 1. I still have that plus 1 out there. So now I've got rid of one of the sums, and I'm ready to split this over the next sum. Yep.
Could you explain again how the comparison in the outer loop gets counted?
Yep. So what are we saying? So the number of comparisons I do here is equal to the sum from I equals 1 to n minus 1 of the sum from j equals 1 to n minus I of 2. So this thing here counts the inner loop comparisons. So that counts everything underneath here. Is that okay? Okay. So then I have this plus 1 here, and this counts how, oh yes, so sorry, there is another plus 1 here. Yes, like that. Yes, so that plus 1 is what counts the outer for loops comparisons. Yes, my mistake. All right, so in fact, this thing here should be a plus 2, and that thing there should be a plus 2. All right, sorry about that. All right, so what I have now is, well, now I actually have this even easier. I can factor out a 2 to get the sum from I equals 1 to n of n minus I plus 1. I still have that plus 1. So now I solve each one of these individually. So this is 2 times the sum from I equals 1 to n of n minus 2 times the sum from I equals 1 to n of I plus 2 times the sum from I equals 1 to n of 1, and then I have this last plus 1. This looks much worse, but it's not, because although I have more sums, each one of them is simpler. So let's do this. The sum from I equals 1 to n of n is just n squared, right? There's n terms, and they're each equal to n, so the sum is n squared. Is that one okay? Yeah.
Why did you get rid of
Oops, yes. Yeah, so this will be 2 times n minus 1. Yeah, good catch. Yeah?
And I didn't get why the inner for loop is in comparison, because you get taken to the one right.
Yeah, but then there's also the for loop itself that needs a comparison to make sure it's less than the upper bound of the inner for loop. So I need one comparison here to make sure that j is less than n minus I.
But don't you already have that in
Yeah, that's this.
But then the
Oh, so I need that to count the outer for loops, exact same issue. Yeah?
Where did each of the 3 plus 1 come from?
Each of the 3 plus 1s. So this one comes from the fact that I need to exit the outer for loop. That costs me 1. This one comes from the fact that I need to exit the inner for loop. That costs me 1 for every single iteration of the outer for loop. Right? Because every time I'm in the outer for loop, I have to exit the inner for loop once for every iteration. And then this last plus 1 comes from the fact that for every single iteration of the outer loop, I need to do one comparison to make sure that I is less than or equal to n minus 1. Right? So I'm going to do this I is less than or equal to n minus 1 check n minus 1 times. So there's a 1 in there. And I'm going to do this extra plus 1 n minus 1 times because I exit the inner loop in every single iteration of the outer loop. And then this last plus 1, well, I only exit the outer loop once because once I do that I'm done. So that plus 1 only happens once. Other questions? All right. So, moving on. So these should all be n minus 1, sorry. So now I have 2 times the sum of I equals 1 to n minus 1 of I. What's that going to be equal to? 2 times n minus 1. So the problem here is that I is the index of summation. Yeah? Yeah, so in general, if this sum were all the way up to n, it would be n times n plus 1. Because I stop at n minus 1, I lose that last term. So you can do that a couple of ways. You could say it like this. You could say that it's n times n plus 1 over 2 minus n. Right? Because instead of summing all the way up to n, you're summing up to n minus 1, so you just chop that last one off. Equivalently, you could just sub that in and say it's n times n minus 1 over 2. And if you simplify this, that's exactly what you get. So I'll leave it like this for now, and we'll see that that's what we end up with later. All right. The third term, 2 times the sum from I equals 1 to n minus 1 of 1. Well, that's easy. That's just 2 times n minus 1. And we have this last plus 1 out here. So we're making some progress, and this is why we did all that stuff on summations, is so we'd be able to do this. So now you could stop here, although it's a little bit more illuminating if you clean this up a little bit. So let's try doing that. 2n times n minus 1 minus, well, that 2 cancels with that, but we still have the 2 out there. So we have n times n plus 1, and then plus 2n. Right? Only the first 2 cancels with that. I still have the other 2. And this is a plus because it was a minus and a minus. That's a very, very easy mistake to make, is to not notice that. And then we have a 2 times n minus 1 out here, plus 1. All right. So, can we do any more cleaning here? Well, we have 2 times n minus 1 minus n times n minus 1. So that's just n times n minus 1. Plus 2n, and then we have plus 2n minus 2, plus 1. So that's n times n minus 1, plus 2n, plus, I'll change that in one go, I guess, plus 4n, minus 2 plus 1 is minus 1. Okay, and if you really wanted to finish this off for whatever reason, that's just n squared minus n plus 4n is plus 3n minus 1. And now this is somehow easier to understand. What does this look like? Well, it's quadratic, so it's a parabola. And that kind of makes sense if you think about it, right? Because the outer for loop goes about n times, the inner for loop goes about n times, so in total it should look about like n times n, which is n squared, and we're not too far from that. Yeah?
So this can partially become the comparison.
Yes. Yeah. So you could also do something similar to compute the number of swaps done. It's a very similar idea. It's not too illuminating, so I'm not going to do that as well. Other questions? Yeah. This 2n, because right here, if you expand this out, you get 2 times n times n plus 1 over 2, so those 2's cancel, but it doesn't cancel here. So when I expand this out, I get minus 2 times minus n, which is plus 2n. Other questions? Yeah?
So this fails for an empty list?
So yeah, so what happens with a negative list is, yeah, this does not work for a negative list. You can fix the algorithm to make it work for a negative list, but this particular one will just do nothing for a negative list. It assumes that there's at least one thing in it. Yeah. Other questions? All right, so that's bubble sort. And notice in bubble sort, at least the way I've coded it here, no matter what happens, the number of comparisons is always the same. There's no way to sort of be lucky and exit early. You can change bubble sort slightly to take advantage of maybe finishing early, but this one doesn't. So it's always this. It's always n squared plus 3n minus 1. All right, what about insertion sort? So for those who don't remember, I'll write down the pseudocode again, although it is the same as last time. So we have insertion sort, A1, A2, all the way up to AN. And it works like this. For j gets 2 to n. Do the following. Set k to be aj. Set I to be j minus 1. And while I is bigger than 0 and ai is bigger than k, do the following. Set ai plus 1 to be ai, and decrease I. And then at the very end of that while loop, set ai plus 1 to be k. Okay, that was insertion sort. I went through an example of how it runs last time. I'm not going to do it again. What I'd like to do tonight is actually analyze this thing to see how it compares to bubble sort. And I want to know, is this better or worse? So let's do the usual thing and find our comparisons. So there's one comparison here. There's one comparison here. There's one comparison here. Another one there. Those are all the comparisons. Questions about that? All right. So this one's a little bit more complicated. Why is this one more complicated? Yeah. Yeah, we haven't seen what to do for a while loop. And the thing that makes it difficult is not the I bigger than 0, because I'm decreasing I every time. So if it were just that, it's essentially a for loop and we'd be fine. The thing that makes it tricky is this AI bigger than k, because we don't know when that's going to happen. That depends on the list. Right? It depends on what's in the list, whether or not that comparison will be true. And the truth of that comparison affects the number of iterations. So that's the issue. Remember, the rule is we're interested in worst case analysis. So it doesn't really matter what the list is. We ask ourselves, what's the largest number of iterations that this thing could go through? So what's the maximum number of iterations? That's what we're interested in. So let's start going through this thing. So we use one comparison in the for loop, right? That's the first one, plus one to exit, as usual. And now we look at the inner loop, and we ask ourselves, what's the absolute worst thing that could happen? So I'll just call it the while loop, actually, because they're different types of loops. Well, I know that no matter what, yeah.
Is there no plus one to exit the while loop?
Possibly, it depends on the while loop, but it's not like in a for loop where it's just automatic, you put it in every time. I'll be careful about how I analyze it, and we'll see something basically like that comes into play. It's just a little bit more complex for while loops. So the worst thing that can happen in a while loop, in this particular while loop, is that I starts at j minus 1, and every time I go through the while loop, I decreases by 1. So the worst thing that could happen would be if I went all the way from j minus 1 to 0. That would be the worst thing that could happen, because the only other thing that could happen is if ai bigger than k were no longer true and I left early. Right? So if I leave the while loop because this second condition is true, I'm only going to be better. And I want the worst case. So the worst case is I start at j minus 1 and I go all the way down to I equals 0. Right? That's the worst thing that could happen. Anything else, I would leave the loop sooner. So the worst case for the for loop is that I goes all the way down to 0. And if that happens, then how many comparisons do I do? Well, that's a complicated question. How many iterations do I do? So I would do j minus 1 iterations. Okay. And now I need to look at the number of comparisons I do. How many comparisons do I do per iteration? 2, right? I need to check that I is bigger than 0 and ai is bigger than k. Whoops, 2 comparisons per iteration. And now we need to think what happens when we exit the loop. So in a for loop, this is usually pretty automatic. In a while loop, we need to think how many comparisons do I need to do to exit this while loop? 2. So maybe the answer is 2, right? Maybe I do this one and it turns out to be true, so I need to check this one and see that that is the one that is false. Right? So maybe I go all the way to the end and then the last one is the one that hurts me. Yeah?
Just one because we go all the way down to 0 for I.
So the other sort of train of thought you might have is that you go all the way down to 0 just for I, and then you're done because this is the one that's false, and maybe you don't have to make the other comparison. Yeah?
So I guess it would depend on what language you use, because there are some languages where if you have an and the first one is false, you'll quit immediately, and there are some languages where it won't.
Yeah, so some languages, like you said, when they do something called short-circuiting, and they say, well, if I'm evaluating a conjunction, I know, because I took John's Comp 1805, that if the first thing is false, it doesn't matter what the second thing is. The conjunction is definitely false. So some languages do that. Not all of them do. This is pseudocode. It's not clear. I'm going to say it doesn't short-circuit. So I'm going to say it maybe has to make both of those. And that's really all I can do, because I don't know what language you're going to go home and code this up in. So if I want to do an honest-to-goodness worst-case analysis, I have to assume that your language doesn't do short-circuiting and both of these will be evaluated. All right? If I'm wrong, well, you should be happy because you do even less work. I'm giving an upper bound on the amount of work done. So I do 2 comparisons per iteration plus 2 to exit. All right. So what does this mean? What's the total number of comparisons that I do? Well, how many iterations of the outer for loop are there? Right, so it goes from 2 to n. So the number of comparisons done is the top thing minus the bottom thing plus 1. So n minus 2 plus 1 is n minus 1. So if I just wanted to write down the answer without doing this sum stuff, so I'll show you how to do it this way for this one. I do n minus 1 iterations of the outer for loop. In each one of those iterations, I do 1 in the for loop, right? I do 1 to check that j is less than n, or less than or equal to n. Okay. And now I go into my while loop. How many iterations of the while loop do I do? Well, in the worst case, I do j minus 1. Right, that's the absolute worst case. All right, and in each one of those iterations, how many comparisons do I do? Well, I do 2, right? I do I is bigger than 0, and ai is bigger than k. So 1 plus 1. This one is I bigger than 0. This one is ai bigger than k. And then I might have to do 2 to exit the loop. And then I'm out of the while loop, and then to exit the for loop, I might need to do 1 more. This last one is to exit the for loop. So this is how you would approach this if you didn't want to go to sums. For this one, you could make a strong argument of going either way. Yeah? Yeah. Yeah, so that's this, whoops, this thing here. If I have the sum from I equals, let's say, x to y of something, the y is the top thing, it's the upper limit of the sum. The x is the lower limit of the sum. The number of terms in this sum is going to be y minus x plus 1. That's how all sums work. Other questions? All right. So the issue then becomes, if you try to evaluate this expression, you don't get something meaningful because your answer will be in terms of j, and your answer should not be in terms of j. Right? That doesn't make any sense. J is just some temporary variable. So that's why you actually do, after you've got this, you do sort of have to change this into sums a little bit. All right? So really what we want is the sum from, what letter do I use? I use j equals 2 to n of the following. 1 plus the sum from I equals, well, I starts at, well, it goes from j minus 1 to 1. So 1 to j minus 1 is just the same. Doesn't matter which direction. And in there we get 1 plus 1. And then we get plus 2 to exit, and then plus 1 to exit the other one. So, I mean, does everyone see that the top expression doesn't make any sense? Conceptually, it makes a lot of sense, but mathematically, that's not going to cut it. Because if you simplify that expression, you'll get your answer in terms of j. Right? That's not a thing. Any questions about that? So this is what you need to do. Because this thing here, the top one, you can't have an answer in terms of j. Right? You can only have an answer in terms of n, because n is the thing that's actually given to you. Right? You know something about the list. That's part of your input, if you like. So now what we do is we just work on the sum. So sooner or later you will have to go to sums. It's just this time we deferred it a little bit. But luckily this sum isn't too bad. So the sum is j equals 2 to n of 1 plus, well, I can just simplify this in one go and say 3 plus the sum of I equals 1 to j minus 1 of 2 plus 1. All right, so the sum from j equals 2 to n of that is just this. Whoops. Yeah, plus the sum from from j equals 2 to n of the sum from I equals 1 to j minus 1 of 2 plus 1. All right, all I'm doing is splitting the sum. Usually I don't do it this way. Usually I would simplify the inside first. But if you don't want to do it this way, or that way, this is how you do it. Yeah?
Is that first sum, is that an I or a J?
Always a j. I'll make it clear, sorry. J. Yeah. Yeah?
Doesn't this have the same problem where you figure
No, because this thing out here, so this inside sum will be in terms of j, but then I have this this outer sum to get rid of the j, basically. So this will only be in terms of n at the end. Yeah, I just split that up. Usually I've done the examples where I simplify the inside first before going outside. I'm doing it the other way this time just so you can see it. Yeah? Yeah, exactly. All right, so let's work on this. The sum from j equals 2 to n of 3. Well, that's just 3 times the number of terms, which is n minus 1, because it's n minus 2 plus 1. This thing here is the sum from j equals 2 to n of, well, there's a couple of ways you can do this. The easiest way is to bring the 2 all the way out and leave it like this for now. Oops. So now we say 3 times n minus 1 plus 2 times the sum of j equals 2 to n. The sum of I equals 1 to j minus 1 of 1, well, that's just j minus 1. And I have this plus 1 up there. So far, so good? Yeah?
Why is it starting at j equals 2?
Yeah, because the pseudocode says j gets 2 to n. So if you go back to when we were defining insertion sort, the idea was, remember, we're growing these things left to right such that the front bit is kind of already sorted, and the first thing is already sorted with respect to the first thing. So I don't need to insert the first thing. All right. So now we do a bit more work. We have the sum from j equals 2 to n of j minus 1. We don't quite have a formula for that. So what we do instead is we say, let's split it up. J equals 2 to n of j, and, minus j equals 2 to n of 1. The sum from j equals 2 to n of j, what's that going to be? We almost have a formula for it, just a little bit different. So what can we do? Yeah? So you could approach it that way. Yeah, so if we sum up from j equals 1 to n, we'll get n times n plus 1 over 2. But the problem is that includes 1, but we shouldn't have included 1. So to fix that, you just subtract 1. Right? The sum from j equals 2 to n of j, that's the same as the sum from j equals 1 to n of j, but then you subtract off that 1 at the end. Right? That's all you have to do for that. And then we have the sum from j equals 2 to n of 1. Well, that's just n minus 1. And you have to remember to keep your brackets straight. It's very easy to make a mistake here. And now we're happy because all of these summations are gone. Yeah?
So you could rewrite j equals 2 to n as j to n minus 1.
Sorry, say that again?
You could rewrite the j equals 2 to n
Yeah.
as j equals 1 to n minus 1.
No. So in that case, so you want to write it as the sum from j equals...
I'm wondering why you subtract 1 like how that works.
So all it is, think of it this way. The sum from I equals, let's say, A to B of something is exactly the same as the sum from I equals 1 to B of something minus the sum from I equals 1 to A minus 1 of something. Yeah, that's one of the additives we covered. So all it is splitting up the order you look in the terms, and then you just rearrange this, and that's exactly the law I applied there. The something is j, the a is 2, and the b is n. That's all you do for that. All right. So let's clean this up a little bit. We're finished the summation, so officially we're done. But I want to compare these two things, so they should have similar forms. So I have a 3n minus 3. I have a 2. Well, I'll just expand this out. N times n plus 1 minus 2 times n minus 1 plus 1. And I'll make this a little bit more big. N times n plus 1 minus 2 minus 2n plus 2 plus 1. Remember, I have a minus here and a minus here, so that becomes a plus. And I'll clean this up some more. 3n minus 3 plus n squared plus n minus 2 minus 2n plus 2 plus 1. So now we just have to collect like terms, right? This is fully expanded out. So we have n squared, which is right there. Next we'll look for the n's. There, there, there. And then we'll look for the constants, which are there, there, and there. All right, so we have n squared. We have 3n plus n is 4n, minus 2n is 2n. And then minus 3 minus 2 is minus 5, plus 2 is minus 3, plus 1 is minus 2. That's how you can do that. Yep.
Let's switch ones up. How do you go from sum of 1 to n?
Yeah, so each term is 1. So this sum is the exact same as the number of terms of the sum, because each term is 1. So the number of terms in this sum is n minus 2 plus 1, which is n minus 1. All right, so this is the worst case number of comparisons from insertion sort. So let's think about this. Worst case insertion sort equals n squared plus 2n minus 2. Worst case bubble sort. Well, let's figure it out. It was n squared plus 3n minus 1. N squared plus 3n minus 1. So how do these two algorithms compare? Insertion sort seems like it's faster when you count comparisons. Yeah, yeah.
If you did a really big n, if there are a lot of elements, it wouldn't really matter very much because the n squared would take over.
Exactly. So yes, it's true that insertion sort in the worst case is doing fewer comparisons than bubble sort. That's true. Fine. The more interesting thing, though, is that these are both parabolas. And notice that as n gets really, 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 really big, n squared is way, way, way bigger than 2n minus 2. Right? And it's also way bigger than 3n minus 1. So as n gets larger and larger, the only thing that matters is the fact that it's n squared. In fact, even if one of them was 2n squared, it wouldn't really matter that much. Right? Yeah, maybe it'd be twice as big, but it's only bigger by a constant factor. So you can think of that the following way. If I make n a little bit bigger, that's still not going to be as much as having another factor of n. Right? So 2n squared, that's way less than n cubed. Multiplying by 2 does almost nothing compared to multiplying by n. That's the important thing. So all this to say, insertion sort, yeah, it uses fewer comparisons than the worst case. That's true. But on the other hand, these functions aren't that different. Right? They're both parabolas. So in some sense, these algorithms are roughly equivalent in the worst case. Because what could happen is insertion sort could run much faster. There's always that possibility. Because remember, in insertion sort, we analyzed it in the worst case. In the best case, maybe it's much better. But in the worst case, they're basically the same. So both of them have an n squared. And the n squared is much bigger than anything else in those functions. So those other little things don't really make much of a difference. So as n grows bigger and bigger, the n squared part is the part that matters. And this is what we do when we analyze algorithms. So I told you that we care about the worst case, and that's true, we do care about the worst case. The other thing we care about is what happens when n gets really, really, really large. We actually don't care so much what happens when n is small. Right? If you're sorting a bunch of numbers, and if you have 10 of them, and if it takes 10 seconds or 11 seconds, I mean, who cares, really? That's not a big difference. The important thing happens is, well, what happens when you have billions of elements, right? And then a small difference in efficiency in your algorithm, say one extra comparison, well, if you compound that over the total number of iterations of those loops, that becomes huge. So that's why we care about large n. And if you think for a little bit about what it means to care about large n, what it really means is you care about how the function grows over time. So in the worst case, those behave approximately the same because we only care about large n. Now, maybe you think that I'm being a little bit imprecise when I say that. We only care about large n, right? This 3n minus 1 doesn't matter. This 2n minus 2 doesn't matter. Yeah, right now, that is a little bit imprecise. And I'll fix that very, very soon by giving you a very rigorous definition for what this kind of growth means. Before I do that, though, I want to stress how painful that the two analyses we just did were. Right? That was really annoying. I didn't really like doing it. Bubble sort and insertion sort, that's an awful lot of detail. Right? Counting those comparisons, worrying about when there was a +1 to exit the loop. If you think back to what I said after I analyzed bubble sort, I said, well, there's two for loops, they're nested. They both roughly go from 1 to n, so when I have them inside of each other, it should be about n times n is n squared. Right? And that logic, just there on its own, it works. Right? I said it should be about n squared, and the answer is it's about n squared. So that tells you it should be possible to get answers like this without going down into the nitty-gritty and actually computing the exact number of comparisons done. That information isn't useful to anyone. Because the first thing we did when we wanted to compare how insertion sort and bubble sort worked was we ignored everything past the n squared. So why did we go through all the trouble of coming up with those? And the answer is, you don't. So half the reason I showed you these analyses was to prove to you that what I'm about to talk about next is in fact useful. So the thing I'm going to talk about next is the growth of functions. So the growth of a function is determined by the highest order term in that function. And I'll define what that means. So the idea is if you add together a bunch of terms, so x plus x squared plus x cubed plus x to the 4, as the function inputs grow larger and larger and larger, the function itself grows about as fast as the largest term. Right? N squared grows much more quickly than n. So when n is very large, the thing that matters most is the n squared. That's what makes the biggest difference. At least for large values. At least for large values. So as an example, let's say that we have some function f of x, and it's equal to x squared plus 1. This function grows about as fast as g of x equals x squared plus 2. Right? It's just a little bit slower, but as x gets very, very large, plus 1 or plus 2 doesn't make a big difference. Right? If I said to you, this house costs, $500 million and 1 cent, who cares, right? It's about $500 million. All right. So, furthermore, if I had a function h of x, and it was x squared plus 2x plus 1, that is also about the same, because for large x, x squared is way bigger than 2, and it's also way bigger than 2x plus 1. So this triple greater than, that's way bigger than. It doesn't really have a rigorous definition. All right. So similarly, this shows you that when you add a bunch of things together, it doesn't really make a big difference. The same is true when you do multiplication, as long as it's multiplication by a constant. So constant multiples don't matter that much. So if I have f of x equals x squared, that grows about as fast as g of x equals 2x squared. Because for large x, think about what would make a bigger difference. So imagine some huge, huge value of x that I'm going to input into this function. What would matter more, if I increased x or if I increased 2? X, right? That'll have a much bigger impact. If I change the 2 to a 3, it'll grow 50% bigger. If I change x to x plus 1, it'll grow way bigger than 50% bigger. Right? So the x is the thing that matters. And the same is true even if it were 100x squared. Right? It doesn't matter which constant it is, only that it is a constant. And the idea is because multiplying x squared by a constant doesn't really change it that much, at least compared to increasing x. Yes?
Does this also work for exponential? Should the x above the 10 should the x?
That becomes a little bit more difficult. We'll need some tools to analyze that a little bit more carefully. I'll show you how to do it. Yeah? Sort of. It's a little bit more rigorous than that. Yeah. Yep.
Say g of x takes a minute, but h of x will then take 50 minutes, right? So it is kind of actually
It is different, but as x grows very, very large, the thing that matters more is the x squared than whether it's multiplied by 2 or 100. For sure, absolutely, h of x is bigger than g of x. No question about that, and it's also bigger than fx. What you need to concentrate on is what happens while x is increasing. What makes the biggest difference? X squared does more so than 2 or 100. Other questions? All right. So the reason is because for large x, multiplying x squared by a constant doesn't change it very much compared to increasing x. You think, what makes the biggest difference? So essentially what this means, and I'm not being fully precise yet, I'll get there. Essentially what this means is when we want to compare these functions, we're looking at what the shape of the function's curve looks like. So if we have, let's say, 3 graphs, and this one is f of x equals x, this one is f of x equals 3x, and this one is f of x equals 1/3 x. These functions these functions aren't the same. They're 3 different functions, but they all grow the same, right? They're all lines. Yes, they have different slopes, but they're all lines. And that's really what we're interested in. That's what I say. That's what I mean when I say how do the functions compare as n grows large? Well, what does their shape look like? How do they grow? And these all grow like lines grow. So all of these functions are lines. That's the main thing. Their slope and y-intercept do not matter. at least in as much as we care about defining how they grow. So it might seem weird to ignore all this other information. We do it for two reasons. One of those reasons is what I've already described, because it's too much work to get that much detail, and we don't care about that detail anyway. The other reason is because only caring about the highest order term without those constant multiples, well, that's sort of like ignoring the differences between hardware differences between my computer and your computer, operating system differences. If the CPU is twice as fast, the algorithm will execute usually about twice as quickly. But that doesn't mean that the algorithm is twice as good on one computer versus the other computer. It's the same algorithm, right? So if you plotted the amount of time it takes for the algorithm to run on one computer versus another computer, they would be different lines if one computer were faster than the other, but they would both be lines. And it sort of has to be that way. If you want to compare algorithms on any sort of reasonable platform, you need to be able to have some consistent definition of what performance is, right? And it doesn't matter that it runs a little bit faster on one computer versus another computer. The important thing is the behavior as the input sizes grow larger and larger is consistent. They're both lines. It doesn't matter what the slope is. They both behave like lines. So only caring about highest order terms. Corresponds to ignoring differences in hardware, implementation, etc. That's why we do this. So even if the CPU is twice as fast, the algorithm still behaves the same way, even if it executes faster. So does that distinction make sense to people? Is that okay? All right. So let's be a little bit more precise. So to be more precise, I'm going to introduce something called big O notation. And this is something you might have seen before. I know Pat talks a little bit about it in his 1405 if you're coming from that. But what he probably didn't do was rigorously define it, and I'm going to rigorously define it. So what I'm about to say applies to any functions, functions that go to the real numbers. Typically, in computer science, we use big O notation in the context of analysis of algorithms, but it works for any functions. So when we're analyzing algorithms, we usually say the running time of the algorithm is some function of the size of the input. But what I'm about to say works perfectly fine for any functions. So let f and g be two functions. And usually we say it's either from the integers to the reals, or sometimes it's from the reals to the reals. Doesn't really matter for our purposes. We say that f of x is big O of g of x. So I'll write that out. Fx is big O of g of x. If the following inequality holds, so if there exists, constants c, which has to be positive, so bigger than 0, and k, which also has to be bigger than 0, such that the following thing is true. F of x is less than or equal to c times g of x for all x bigger than or equal to k. Maybe just to be completely clear, I won't put those extra brackets in. C is not a function, it's just a constant. So c times g of x for all x bigger than or equal to k. And one thing we typically do in computer science, because f of x will almost always refer to some number of comparisons, I'm going to add the restriction that it has to be positive, or non-negative, say. Because in our applications, f will usually count the number of comparisons, and it doesn't make sense to do a negative number of comparisons. So that's why we usually add this restriction. All right, so this is really weird, right? This is not at all clear why it's related to what we were just talking about. But if you'll bear with me for a second, we'll get there. So we call C and K witnesses. So when I ask you for witnesses, what I mean are C and K. We can write a few different things. Technically, we should write f of x is in big O of g of x, because big O of g of x, if you think about it for a while, you'll see that it kind of has to be a set. But not many people write that. We could also write fx is equal to big O of g of x. That is technically incorrect, but if you write it, everyone will know what you mean. So it's okay. Typically, to get around the issue, I will just say fx is big O of g of x. I like that style. Technically, this one is more correct. This one is technically incorrect, but everyone knows what you mean. So when I say fx is big O of g of x, what I mean is that after a certain point, after a certain value of x, f is always smaller than g by some constant multiple. Okay, so what that means is this. fx is big O of g of x means that after a certain value of x, f is smaller than some constant multiple of g. So fx, I should say, is smaller than some constant multiple of g. So if we look at this graphically, I'm only going to draw the upper right quadrant because everything's positive. So we have some function here, f of x, and what it's saying is that f is always smaller than some constant multiple of g. So maybe that's my g of x. This point here is where they cross. That's k. And notice that f is always smaller than some constant multiple of g. In this particular example, that multiple is 1. In general, though, f could be above g, and it would still be true as long as it was only at most twice g, or at most 3 times g, or 4 times g, or some constant multiple. So we'll see plenty of examples of this. So here's a first example. I want to show that 5x squared plus 10x plus 3 is big O of x squared. That's what I would like to do. Whenever you're asked to show that a function is big O of some other function, what you are really being asked is to give C and K. So if I ask you on a test or an assignment or an exam to show that something is big O of something, you have got to say the C and the K. There are other ways of doing these questions. In particular, you can solve these using limits if you're comfortable with calculus, but not in this class. So this class is discrete math. It has discrete in the title, so we will not be using calculus. And the reason I insist on this is because I've taught this course lots of times, and consistently what happens is the students who use the limit approach don't fully learn what's going on. So that's why I'm saying no limits in this class. All right, so if I want to show this, I need to say what C and K are. And what I'm shooting for is, well, this thing here, if you compare this to the definition, this thing here is my fx, this thing here is my g of x. So I want to show that fx is less than or equal to c times g of x for all x bigger than or equal to k. I get to pick c and k. They can be anything I want as long as they're bigger than 0. I just need to prove that they work. So let's do that. I want to prove that an inequality is true. So I start on one side, 5x squared plus 10x plus 3. And now I want to show that this is less than or equal to c times x squared. So the typical trick for this is the following. I want to write less than or equal to something. So I need to write something bigger now. I have 5x squared. I'm going to leave that as it is. 10x is less than or equal to, so I have 5x squared. 10x is less than or equal to 10x squared. Is that true? Right, if I multiply by x, I get something bigger. That's actually true as long as x is bigger than 1. Okay. And I also have this 3, but if I multiply by x squared, I also get something bigger. That's actually only true as long as x squared is bigger than or equal to 1. Right? If x squared were like 0.5, then you get something smaller than 3. All right, so now I have 5x squared plus 10x squared plus 3x squared. So that's nice. I have 18x squared. So this thing here, this 18, that's going to be my c. Because if I look up at the definition of big O, I wanted to prove that fx is less than or equal to c times g of x. Well, g of x is x squared, which is right there. And f of x is this. So this shows that fx is less than or equal to c times g of x, and the value of c is 18. So the last thing I need to do is figure out what my value of k is. So k, remember, I need this inequality to be true for all x at least k. And I already have some restrictions here. I know that x has to be at least 1, and I know that x squared has to be at least 1. So if I say that x is at least 1, then both of those are true. Right? If x is at least 1, then x is at least 1. And if x is at least 1, then x squared is at least 1. So both of those are true. So as long as x is at least 1, well, if I look at the definition, it's for all x bigger than or equal to k. So that means this 1 here is exactly my k. So therefore, 5x squared plus 10x plus 3 is big O of x squared with witnesses c equals 18 and k equals 1. So this is how you would answer that question. Yep. So the idea is I'm shooting for something on the right that just has an x squared. And I have these terms that involve x and just 3. So I need to get rid of them somehow. And the way I get rid of them is by turning them into x squareds so I can collect them and use that as my c. Yeah, so there's tons of ways to do this. This is not the only way of doing this. I will do lots and lots of examples to show you all the sort of common tricks for doing this. All right. So that's it for today, guys. Good luck on your tests for those of you who haven't written, and we'll see you next time.